On number 4, we're given 4 differential equations and told to match the equation up with the graph. Notice that each one of these we have a function of y with respect to t. So we have our y-axis goes up and down, our t-axis goes left and right, and we can match these up in any order. Let me just start with A, and I'm going to find critical values by setting the derivative equal to 0. Here on A, that's going to tell me that sine of y is equal to 0, and I know that sine of y is equal to 0 when y is 0 or pi or 2 pi, negative pi, negative 2 pi, and so forth. I also know that sine of y is positive. Sine of y is greater than 0 when I'm in the first quadrant and the second quadrant. So when y is between 0 and pi, and sine of y is negative when we're in the third and fourth quadrant. And because here I have positive values and negative values, I'm going to put that as between negative pi and 2 pi, and 0. So let's see. My critical value is at 0, at pi, at 2 pi, and this is for y. So it could be here, could be here. Well, here would be pi, possibly, but then 2 pi would be down here, and we don't have a critical value down here. If this were pi up here, that would be our critical value, somewhere around here. It's kind of hard to see the scale. And negative pi would be here. That makes sense. If I look at this third graph, y equals pi, there's no critical value up above the x-axis, not one that you can see, and it doesn't look like there is one. And also here for the last graph, you don't have any critical value that goes straight across. So on my second graph here, I'm betting that there's a line somewhere right around here at y equals pi. And another one down here somewhere where y is equal to negative pi, and actually at 0 also. Y equals 0. And then let's double check this. The sign is positive, so our slope is going to be positive between 0 and pi. Between 0 and pi, notice that our slope is positive. It's increasing. And the sign is negative between negative pi and 0. So between 0 and negative pi, my slope is negative. I'm going down in this region. Okay, so this is our graph A. Now, for graph B, this is very similar, except we have the derivative is sine of t instead of sine of y. And so if I set sine of t equal to 0, I'm going to get the same values that I got over here, except they'll be there for t. I'm going to have critical values at t equals 0, t equals pi, t equals negative pi, and then other values. And sine of t is positive. when t is between 0 and pi. Sine of t is negative when t is between negative pi and 0. Should be a t. Okay, so I want to look where t is equal to 0. That's going to be on the y-axis. I'm going to want to look for little horizontal marks. And notice that the only place you see those are on this last graph. So let's verify. This is where, this is our y. That's our t. This is where t is equal to 0. And then where t is equal to pi, those would be these marks right here where we reach our maximums. That's t equals pi, and t equals negative pi is over here, again where we have these maximums. And then let's verify increasing and decreasing. The function is increasing, the slope is greater than 0 when t is between 0 and pi. Between 0 and pi, notice that our line goes up. Increasing here. And then between negative pi and 0, the derivative is decreasing, less than 0. And in this region, between negative pi and 0, our line is going down. So this is graph B. Now, graph C, we can find critical values by setting the derivative equal to 0. Y squared minus 2y equals 0. Could factor that to get y times y minus 2. And our critical values are at 0 and at 2, where y is equal to 0. See, notice that on this third graph here, y equals 0. You don't have those critical values except for at this one point right here. But over here on the first graph, you do have, looks like this is an attractor. Solutions are coming towards it at y equals 0. And then at y equals 2, that's going to be this up here. And you can double check to see that the slope is negative in this region and positive in the upper region and positive in this lower region. On this last graph, if I set t minus 2 equal to 0, I get t equals 2. And a critical value at t equals 2 that's showing up, let me label this first, that was a C. That's showing up right here. That's t equals 2. So notice just by locating the critical values, you can see pretty much which graph it is. You should double check increasing and decreasing. Where is the derivative positive and where is it negative? But we've done a good job of identifying these graphs the way it is. So there's also a part here where it asks to sketch the unique solution for the initial value y of 0 is equal to 1. I'll try that with a highlighter. So here, y of 0 is equal to 1. Maybe I won't do a highlighter, that's a little bit too big. Y of 0 equals 1. Notice that on this graph, that gives you the point 0, 1 is here. And from here, if you just follow the slope, you're going down and then leveling across. On the second line, this is 3.14, so 1 is probably right about here. And from this point, you can see that your graph is going up, and then it's going to level out right here along y equals pi. Here it's kind of hard to see what the scale is, but if we this looks like 2.5 there, so 1 would probably be about here. And notice that from here the graph goes down and then comes back up. Looks like a parabola. And then on this last one, y of 0 equals 1. Again, that looks like 2.5. So 1 is probably about here. And your graph goes up, reaches a maximum, and then comes back down again. If this is the initial value, you don't want to graph to the left. You want to just graph to the right.